if you look at the PAXOS, so in PAXOS family of the distributed algorithm, right? So in this, we'll try to discuss the vanilla PAXOS, which was proposed by the Lamport in 1969. Okay, in that condition, if you see there are 5 nodes. So what is the PAXOS algorithm says in distributed network? If you recall the story, the PAXOS is a distributed consensus protocol, which is basically designed to help a group of unreliable machines or nodes which are agree on a single value. So even in the presence of the crash nodes or network delays or message loss or the partial system failures. So the PAXOS guarantees one is the safety, as we discussed. Okay. So the PAXOS guarantees this safety means no two nodes decide different values. No two nodes that decides the different values. And this PAXOS also guarantees the liveness. So what is this liveness? The liveness is the progress that eventually happens, right? If a majority of nodes are responsive. So what is the key idea of this PAXOS is in distributed systems can still reach the agreement as long as a majority quorum or majority of nodes are alive and can communicate. So why do we need these PAXOS in this fault-tolerant system then? In distributed systems, as we just discussed, the nodes do not share memory. First key point. The nodes communicate via unreliable network because it is an asynchronous network, and the nodes may fail at any time. So the consensus is required for the leader selection, then distributed logs, then replicated database or blockchain ordering and fault tolerant state machines. So without consensus, data inconsistency will be there in the network and split the brain scenario, okay, that incorrect system behavior. So in the roles in this PAXOS, there are 3 rules as we mentioned in our previous lecture also. What are those? One is proposer. The proposer suggests a value, okay, and initiates the protocol. The second one, the acceptors. The acceptors in the network, they vote on proposals and maintains protocol correctness. That means the majority of acceptors are known as quorum. So in this case, there are 3 acceptors are there. So they have the majority of acceptors, means they become a quorum. The third one is learners. So the learners learn the final agreed value. The final agreed value. So if you look at this, in this case, there are 2 proposers. Proposer 1, let us say, proposing let's go for dinner. And second proposer is proposing the value 2, that is let's go for the movie. All the remaining are becomes the acceptors. So the acceptors, that means the votes on this proposal. Shall we go to the dinner or the movie? So they have given their idea in this case, if you recall. Okay. So one is giving the great idea of go to movie, remaining are go for the suppose the dinner. So then later, if this proposer also accepts, so okay, let's go to the movie, then the majority of the acceptors, they voted, they become a quorum. So then the next step, accept this proposer, all the remaining one become the learners. So a node can have any or all of three rules, like maybe the proposer, acceptor, or learner. This is in practice, nodes often act as a proposer plus actor plus learner. So the core PAXOS concept here is the proposal number is the main one. So proposal number means if you look at that, in this case, however, the nodes must know how many acceptors a majority is. So two majorities will always overlap in at least one node. So how that is means if there are five acceptors, the majority it requires three. If there are two proposers are there. But to accept based on the majority voting, at least one acceptor needs to choose, okay, one of two proposers, isn't it? So in basic, the Paxos is based on the state machine replication. I said a small unit, I mean execution code, the automatic running code will be executed by every machine in the network. So the proposers and acceptors maintains the state of the running echo, and whereas they use as the variable like ID, the proposer IDs, where P is the epoch number that maintains the state, and they runs the single consensus. They aim to reach to a single consensus, so they run the code. So once a consensus is reached, the PAXOS cannot progress to another consensus. So to reach the multiple consensus, they need to run this PAXOS multiple times. Right? So let us see this algorithm. Let's assume there are proposers and the acceptors. So the proposer wants to propose its choice. So that is the value. So they must prepare a value. Then they use the message that they prepare IDP to a majority of the acceptors. That's the message. The message will be prepared, created. So this IDP they must be unique across the proposers for each prepare messages. For example, they use their hash values. So to do the hashing, they use the timestamp and proposer ID to generate the proposer message, are we call the prepare ID, right? And then that sends this the prepare ID to all the acceptors or majority of the acceptors. Okay. And upon receiving this, the promises, okay, offer means this proposal number has this unique and increased number every time. Okay, so in this example, it is the round number, suppose 100, and the node ID is the IDP. Whatever node is there, node 1, node 2, node ID will be there. So why this proposal number means it ensures the newer proposal override the older ones safely. So then the quorum or the majority of the acceptors, if there are n acceptors, okay, so from this quorum, at least n by 2 plus 1, okay, must be the quorum. They must become the acceptor or the quorum. So in this example, suppose if there are 5 acceptors, I mean, if there are 3 acceptors out of 5, if there are 5 nodes out of 5, if there are 3 acceptors, okay, they become the quorum or the majority. So in this, what is the first phase here now? The first phase, that proposers choose a proposal number and sends the prepare ID, that is prepare ID 100, to the acceptors. Then an acceptor responds with the promise. Yeah, let's go. They accept with the promise. Okay, with the same ID. So in that, the acceptor responds with this promise if it has not promised a higher proposal number before. At this case, the proposal number is 100. So the acceptor can promise it. It's purely new. It also reports the highest accepted proposal. Okay, it reports that. So the acceptor now promise not to accept any proposal number that is lower than 100 here. So that is the first phase one, the prepare and the promise phase we go. So the next phase is the acceptors. Accept phase we call. So what is that? If proposer receives the promises from a majority, it sends a accept value. It sends the accept value. So that accept value is majority of acceptors accepted value 100. That's, for example, go for the dinner in this case. So the rule for choosing this value is if acceptors reported any previously accepted value, that's the rule. Okay, the rules for choosing the value. If acceptor reported any previously accepted value, proposer must use the value with the higher proposal number. Otherwise, proposer use its own value. So the acceptors accept the proposal, the next step, and notify the learners. So when this acceptor receives the accept this value 100, then accept that proposal, all the remaining become the learners. So once a majority accepts, the value is chosen. Isn't it? Okay. So this is the PAXOS algorithm one. So everyone become the learner. So next time, if any new proposal come, the value, it must be greater than this ID proposal ID. So if the majority of acceptors accept this value, the consensus is reached. So this consensus is reached on the value, not on the IDP. So what is the value? The value is go for dinner here in this case. So the proposers or learners get accept message with this IDP and value, right? So this is the case. So next time, if proposer 2 prepare a ID that 50 with value, some other value, so this round number is less than this round number. So this proposer message will be ignored by the acceptors. Why? Because the blockchain is already increased. The proposer 2 is sending the older block. Is it? Yeah. So then the yeah, good. Okay. Yeah. So the next, the proposer 2 may propose the new proposal with the increased ID, that is 150. So that when the acceptors receive this message, okay, and they check whether they promised with this message or not. If not promised, then if promised, then ignores. If not promised, because it's broadcasting in the network. So now we'll promise to ignore any request which is lower than this IDP, and it has ever accept anything with the new value, then try to accept that value. So that is rejected by this acceptor, and this proposal, which is proposed by the second proposal or second, user, will be accepted. Yeah. So this way, if there are multiple processors, the proposers are there that can be handled to reach to the consensus. Yeah. So it has. So what the proposer will do later that if a proposer, first proposer is accepted the value of ID, I mean 100, so then everyone become learner. The second proposal was accepted by the majority of the acceptors, that is 150, right? So the acceptors, has it ever accepted anything, means assume the accepted ID is equal to the IDA. If the condition is yes, suppose that reply with promise ID, that is accepted ID plus value, and not reply. So in this case, suppose the acceptors says that yeah, we accepted this ID that go for dinner, and the new proposal is promised. So changing their decision. So what the proposer will do now, the proposer 1. So the proposer gets the majority of promise messages for a specific ID, like for 150 here. So that sends accept ID to the majority of all acceptors. So it picks any of its choice. The proposer picks any of its choice. So the proposers, sorry, the choice is whether to say yes or no for promising. Says yes, that picks the value with the highest ID, and no, that picks the value with sorry, with value of its choice. So that choice is given. It is up to the proposers whether want to go with the same value or not. So if proposer wants to accept the value 100, it's up to the choice. Okay. Or say yes to pick the new promise or new propose. Sorry. Okay. So the PAXOS, how majority works means, if you look at, there are two proposers that prepare ID is suppose 100, and saying that let's go for movie proposer, and that will be broadcasted. So the acceptors go with this, and the proposer 2 prepare ID 50 and saying that let's go for dinner. So that is also broadcasted. It is up to the acceptor to promise to which propose. So suppose the second acceptor, she looking at the prepare ID, the prepare ID of proposer 1 is higher than the prepare ID of proposer 2. So then they promise to the prepare ID 100. So if the majority of this acceptor out of 3, if majority of these acceptors they promised on 100, then the ID 50 cannot get through. So these acceptors will ignore this simply. Okay. So then proposer 1 confirms that the impact on liveness is, this is the majority work. So the impact on liveness is the prepare ID 100 that is promised, and prepare ID 150 that is also promised, suppose. So then how it will be adding? For the first one, the promise ID 100 is added. The second one, 150 will be added. So that is the liveness. Eventually, it is growing. The new ones are accepting. So there is no termination guarantees on the PAXOS here. Why? Because the first promise ID 100 is acceptor request 100 for dinner. Okay. So then that is suppose ignored because the new promise came later with the new ID that is 150. Okay. So then it's up to the choice. So what is the time limit between these two PAXOS to regenerate the next prepare ID 200? So there is no termination guarantee on PAXOS. So the majority of accepts in this case, the majority of acceptors that accepts a request with the ID and the value, the consensus has been reached in this case. So the accept request with the lower ID will not be accepted by the majority. That would require a majority of promises with the lower ID, but we got for a higher one, hence the accept request. So the accept request with the higher ID but a different value will not be accepted by the majority. Why? At least one acceptor will piggyback the previously accepted value. That is, just remember, two majority implies that there is a common node. So the consensus is on the value. So we need the ID to maintain the current state of promise and accept so that multiple values do not propagate in the network. Right? So that's the majority part which we observed in this case, like prepare ID 100 and the acceptors promising for 100 prepare ID, and the acceptor is accepting. They are just promising and promising this prepare ID 100. So proposer 1 confirms that the prepare ID 100 is accepted by majority of the acceptors in the network. So this is the election of leaders that whose idea will be selected. So that the accepted ID is 100, and he is the one, proposer 1 become the leader. So for multi-PAXOS applications often need a continuous stream of agreed values and commit the transactions in a replicated database. So each transaction needs a consensus to be agreed upon by the replicas. So they runs multiple instances of the PAXOS with the different round numbers like 100, 150, 200, 201, and so on. So each value is associated with the round number. So if a value is already accepted for certain round, then ignore the accept request for different values under round, suppose 100, right? So in this example, the failure scenario will be while PAXOS works in the failure scenario also. Suppose the second proposer tries with the different value. For example, in this example, yeah. So if the second proposer tries with different value, the acceptors will report they already accepted, the proposal 1. So then the proposal 2 is forced to propose again, or not, means say X or Y. So the important properties of the PAXOS here is safety, that never broken. Only one value can ever be chosen. No two learners decide differently. So in fault tolerance means it works. Okay? This PAXOS works in fault tolerance. How? It works as long as majority of the acceptors are live. So that is fault tolerance. And comes to this liveliness that eventually requires the stable leader. So that's why for stable leader, the leader selection will be done here. So no endless competing proposers. But what are the limitations of this PAXOS then? It is difficult to understand sometimes. Again, it is hard to implement correctly. The basic PAXOS decides only one value but needs extension for real systems. Is it? So this is the overall concept of the PAXOS algorithm with the three actors like proposer, acceptor, and then become the learners. And to maintain the liveliness, the leader selection is required. Yeah. So that is the concept of the PAXOS. The next one will try to address the another concept called raftal, because in PAXOS it is a little bit difficult to understand and the implementation. So in the next lecture, we'll try to discuss the next proposal, next consensus algorithm, the rafta algorithm.